All right, example number 3 is, it gets a little bit scary when you're looking at trig stuff and then you're asked to factor. I mean, it's hard enough to factor when you're just doing regular algebra. They ask you to factor secant squared x minus 1. So what I'm going to do is I'm going to make a side note. Heck, this is going to be a big side note. So I'm going to do it on another sheet of paper. All right, when something like this pops up, what they're wanting you to see is a thing called a difference of squares. And this is mentioned usually in Algebra 2. Difference of squares. All right, so difference of squares. What the heck is a difference of squares? In math, the word difference means subtraction, and squares are things that are squared multiplied by themselves, like 16, 25, or even x squared. So say if you had x squared subtract, and then, I don't know, some square number over here like 16. There's a special way to factor difference of squares, and factoring means like undoing, and we're actually going to be unfoiling this. But here's the pattern, and it's really easy. The pattern is that if it's x squared, it must have been x and x. And then if this is 16, that's 4 squared. It's 4 and 4. And then it's just one is a plus and one is a minus. It doesn't matter which one is which. Just one's a minus, one's a plus. And then the way this works is if you FOILed this back out, if you multiplied these two parentheses back out, you would get x squared minus 16. Just watch. There's x squared. That would make minus 4x. That would make plus 4x, which would cancel it out. And then that would make minus 16. So when you factor a difference of squares, it just follows that simple pattern. Take a look at another one. Let's just go like x squared minus, I'm going to do a big one, 81. So then this would end up being, since it's a difference, it's a subtraction, and both things are squared, it's just x, and then this is 9 times 9, so you're just going to put 9 and 9. Like I said, it doesn't matter where you put the plus, just one's a minus, one's a plus, or one's a plus and one's a minus. That's what you're going to have here, and that's what they're going to want you to see. Now, not every time that they ask you to factor and you see two pieces, is it a difference of squares? But you should always look and go, okay, I've got two pieces. Are they both squared? It's a difference. If that was a plus sign, well, forget it. That's not going to be a difference of squares. But what we have is a difference, and then this is secant x times secant x. And then this is a square. People will forget that 1 is a square because it's really 1 times 1. So the way that you factor this, actually, let's think of it like this. We're not used to factoring trig stuff. So what I want you to do, instead of thinking of it as secant squared x, think of it as just like x squared minus 1. Okay, that's a difference of squares, and that would factor like this. X minus 1 and x plus 1. It's the same concept, except for instead of x squared turning into x and x, secant squared is going to turn into secant and secant. And then you just have your minus 1 and plus 1. So your secant x minus 1 and your secant x plus 1. If I wanted to just throw a real quick other one out here, I could say, let's just say you had CSC squared x minus, I guess I've already decided I'm going to go with 16. So then this one would be, that's the same, similar to x squared minus 16, which would be x minus 4x plus 4. Similar to this, except for instead of x squareds, it's CSCs. So cosecant x minus 4, cosecant x plus 4. And that's it. So if you notice that you have a difference of squares, think, okay, this square and that square, so then it just would be the same as x squared minus 1. And it's a pretty simple pattern to follow. All right, example 3, this is the part B, asked to factor again, but this time, when we go to factor, we have 3 pieces. So we have 4 tangent squared x plus tangent, or now I said x, we have 4 tangent squared theta plus tangent theta minus 3. I'm going to make a side note on this right here. For this problem, so when you see this, what I want you to do is think Think of it like, instead of 4 tangent squared x, think of it like just 4x squared. And instead of tangent right here, let's just call that the x. Instead of the minus 3, well, wait, no. Let's have the minus 3 there. All right, so think 4x squared plus x minus 3. Now, when you do this in Algebra 1 or on Algebra 2, factoring, we're asked to factor it, you would drop a couple of these. And the way that I always teach is, it really sucks when there's a number right here, a coefficient. A problem that doesn't have a coefficient on your x squared is much easier. But the way I learned it, and the way I teach it, is that we do a thing called the Berry method, as I learned it. If you have a, that says Berry. If you have a coefficient right here, then what you do is the Berry method. So instead of putting x and x, you got to put 4x and 4x. It's totally wrong. It's totally cheating, because 4x and 4x doesn't make 4x squared. But using the Berry method, you cheat right now, and at the end, you fix it. So we put 4x and 4x, and then I need the numbers that go here and here. Well, instead of them multiplying to this, they don't multiply to that. You actually connect your 4 and your negative 3, so they have to multiply to negative 12. So whatever the numbers are, they're going to somehow multiply to negative 12. So I just list out all the ways that you can get 12. I don't worry about the negative so much. You got 12 and 1, you have 6 and 2, and you've got 3 and 4. And then the last part is you get all the pairs. You have to choose a pair that you can somehow add or subtract to whatever this coefficient is. So you want to choose one that'll get you so you can add or subtract to 1. So when I'm looking at it, 12 and 1, no. 6 and 2, no. But 3 and 4, I can get a 1 out of it. So put a 3 and a 4 in there just like that. And then decide if you wanted to get a positive 1, how can you make a positive 1 out of 3 and 4? I'll make it positive 4, that right there. But the last part of the Berry method is, remember, we cheated at first because 4x and 4x doesn't make this. So you fix it at the end by reducing these parentheses. If you can reduce it, you must. So what I mean is, if you look at 4 and 3, if you could divide something by 4 and 3, you would. 4 and 3, they don't reduce. So it is just going to be 4x minus 3. But this one, when it says 4x plus 4, I can pull a 4 out of it. So I'm going to pull a 4 out of it. I'm going to put it right here. And this becomes just x plus 4. Oh, x plus 1, I mean. That's just x plus 1. And then with the Berry method, when that 4 that you pulled out, you're allowed to actually just scratch it like it's not there. So I'm going to rewrite it since I did just a terrible job there. So factor, this is 4x minus 3. And then this is x plus 1, like that. And that's what it would look like. So remember, on Berry method, if you had the coefficient at the beginning, last thing you do is, if you can reduce it, you must. You might have to reduce both of them. You might have to reduce one of them. You'll definitely have to reduce at least one of them. So that's how you factor that. Now, how does that relate to our problem? Well, we just did the same problem, but instead of 4 tangent squared x plus tangent x minus 3, we did it with x squared and x and a negative 3. So really, this is going to be the answer, just where you see the x's. That's where the tangents go. Not tangent squared, just the tangent. So your actual answer would be 4 tangent x, or theta, minus 3. And then you would have tangent theta plus 1. So just do it like it's x's. And 4 tangent squared theta plus tangent theta minus 3. Pretend it's 4x squared plus x minus 3. Factor it out. And then put the tangents back in. Just regular tangents, not tangent squared. And that's it. And if it can be simplified, simplify. And if it can't, it can't. As far as I'm seeing, this one is probably good and done right here.